No. Okay.
Colab
So
notebook. So do I just like open up the welcome to Colab thing? Oh, plus new notebook. Never mind. I see it.
yeah, yeah. So this is the Python for AI session. So welcome. And then what we're going to be doing is just going through a guided demo of how to make a AI model using TensorFlow. And then we're going to kind of talk about how to generalize that process. We're going to be using Google Colab for that. All right. Okay, can you guys see that?
Oh, yeah, I can see that.
All right, sounds good. Okay, so the first thing that we're going to be doing is we're going to do our imports, right? So the main one is going to be TensorFlow. So there's two main Python AI libraries, and that's TensorFlow and PyTorch. And so TensorFlow is made by Google and PyTorch is made by Facebook. And in fact, PyTorch is like adapted from a what's it called? A Lua thing for AI. So actually before Python became big, it was like Lua was pretty big, Lua and C++, but then what they've done is that they've converted it to Python just because Python's so easy and modular. And then though Python is slow, what they're actually doing is like they're using C to run like any of the difficult stuff. But TensorFlow, we're gonna do it as TF, and PyTorch is the other one. Now, why are we learning TensorFlow over PyTorch? TensorFlow is like 100 times easier. And actually, what we're gonna do is um, import TensorFlow.keras, right? And that's just gonna be importing something called keras, and that's like the main part of TensorFlow we're using. Normal TensorFlow, that's for more advanced development, I'm gonna be honest, is not useful. You're gonna use PyTorch at that point. But if you're learning, then TensorFlow Keras is amazing. It just makes everything really simple. We're also going to be using NumPy and matplotlib.pyplot. And so these are two very common Python packages for like ML. NumPy lets you do linear algebra, but is generally like how you'd be using lists for this in general. And then matplotlib lets you uh, matplotlib basically just lets you graph stuff, and you're gonna want to run that code. And speaking a bit about the C part I was mentioning earlier, so the way that actually works is there's this thing that's basically its own language, but technically it's in C, and that's called CUDA. Mat, did I spell this wrong? Matplot,
Do we need
matplotlib,
pandas
sorry.
or
Yeah,
huh?
sorry.
We need pandas also or no?
Not for this one. Pandas. Oh gosh, we don't know what pandas is. Pandas is another one that lets you do data, like organize and mess around with data really easily. But generally what you'd be doing is if you do use pandas, it's more for like the pre stuff when you're dealing with the data, and then you're gonna convert that over into like something NumPy or TensorFlow related. So we're not gonna be actually like pulling our own data for this one just because there's none really there. We're gonna be using like a example data set. So same how like your first line of code might be hello world, we're going to be using like a hello world type of data set. All right, so we've got that run. And then what we're going to want to do is use that. We're going to be putting in that data set. So keras, data sets, fashion, MNIST. So MNIST is a data set of numbers. I think I showed it in one of our previous lectures, but it's a data set of like handwritten numbers. And so fashion MNIST is a little bit more complex than that. Rather than numbers, it's going to be clothing. And then let's write this out. I don't know, it's all yellow. work? No, sorry. Okay, this was a little weird, but the way you're gonna want to do this is say fashion mness is equal to this. So this is gonna be equal to some object, and then what we're gonna be doing here is loading in the data. And after we kind of go over the first example, I'm gonna show how you can get data in a different way. But right now we're just gonna be loading in the data. So we're gonna get these train images and train labels. So the images are of course the images we're training on, and the labels are the corresponding like ID for whichever piece of clothing there is. So a shoe might be 0, a dress might be 1, a shirt might be 3, something like that. All
Wait,
right.
I'm
Actually,
still a bit oh,
sorry.
sorry. Wait, so fashion MNIST is like our variable name?
Yeah,
Or
this is the variable name for the thing that we're going to use to load in the data set. Don't
oh, all
worry
right.
too much about it.
And the
Actually,
like data labels are like the names of the things that we're doing?
yeah, so they're like the clothing we're going to be classifying. So actually, here, this is actually the order of everything we're using. So t-shirt, top, trouser, pullover, dress, coat, sandal. And I'll send this in chat, so you don't have to type it fully. Sneaker. Oh. Bag and ankle boot. So that's quite a lot of different fashion accessories, but that's what we're going to be using. And the purpose of creating this list is nothing too complex. It's literally just because it's a computer, so it deals with numbers. Actually, we can see that. So train images. We thought it was like it would be an image, but it's turned into a bunch of numbers as a NumPy array. Train labels. It's going to be a bunch of numbers corresponding to that. And so what this list is letting us do is say 9. So what is that index 9? So we can say class names of 9. I don't think I ran this. Okay, it looks like that's an ankle boot. Something cool I think you can do is you can just say class names of train labels. Oh, never mind. Not for this. Ignore that. Okay, but that's the reason we have class names. And we can see that train images, train labels is as a NumPy data set. And I know someone mentioned before that pandas is like we might use pandas. And so what we'd be doing is we'd be converting pandas into NumPy to make it work better. And there is 10,000 test images and 60,000 train images.
Wait,
So
what's the difference
actually
between
see
a test image and a train image?
what's the difference?
Yeah.
So think of it like train images are the images you're practicing on. Like say it's a test for math or something, right? So train images are the practice problems. You might practice addition, subtraction, and everything. And then the test images are like the test, right? So after we trained on all of that, we did some practice and we kind of understood how it works. We're going to see data we haven't seen before or problems we haven't seen before. So say I practice like 2 plus 2, 4 plus 3, and 5 plus 1. Then on my test, I'm going to get like 3 plus 7, right? It's completely different, but it's seeing, can what you learn in the beginning be generalized? Like, did you actually learn anything or are you trying to memorize it? Because if we try and evaluate performance on the train images, then what we're doing is where the model is just going to memorize everything and we don't actually know if it learned anything. Now what we're going to do is just show the, any questions about that?
I also okay, yeah, so I do have a question. So like for the train images, train labels, why do we have that? Oh wait, never mind. Never mind.
Oh, and the parentheses and stuff is just to show like grouping a little better. There's no reason for to be. There's no
How
real
do you
reason to be that.
separate your things into like different like sections? Like I noticed you
Yeah,
have
it
the
just
6 and
looks
9
a
and
little better.
15.
Yeah.
No, but like how do you do that?
Sorry?
How do you do that? Like, how do you like split it up?
I'm confused. Like split what up?
Like, it separates yours into like different boxes, like one for 6 lines of codes, that goes until the 9th, and then the 15th line of code. Like, does it just automatically do that?
Oh, plus code. That's how you create a new code block.
Oh, thank you.
What I'm doing here is I'm just using PLT to show the first image in it. So that's like an image at index 0. Yay, it's a ankle boot. And you can see that this is, first of all, it's like purple and green. So if we don't want that, we want it black and white. You can do CMap gray, and now it's gray. Another thing I want you guys to notice is I did color bar. So that shows us the corresponding like pixel value for the color. You can see how 0 is black and 250 is white. Or actually, it's 255, sorry. It's just very close to 250. So the thing about that is that numbers, like computers don't like big numbers. You know how we function on zeros and ones. And so we don't want to be using 255. We want to be using something smaller, preferably 1. And so what that's called is normalizing the data. And in fact, the way I'm going to do that is just really simple. I want anything at 0 to stay at 0, and I want anything at 255 to become 1. It's a really easy way to do that, and that's just dividing everything by 255. And we want that for the test images as well. We want the test images to be in the same condition, the same style as the train images, but we want the content of the test images to be different to make sure it's actually learning something. I put the 0.0 so that it's
I'm a bit why do you want them like all black and like divided into like a 1?
so the black is just like there's no reason that we have to do that. That's just so that we can see it like correctly here. Like if you don't like that purple and green look, you can change it. The 1 is because we want to normalize the data. And so computers don't like, so I think we covered this in the lectures, but what's happening is a bunch of multiplication. So what is 2 times 1?
2?
Yeah. And then how much greater is that than the original value?
Uh, the original value being 2 or the original value being 1?
1. So if I have like 2x, how much greater is that than x?
That's 2 times bigger.
No, like, so I have 2 times 1 minus 1. What is that?
That's 1.
Okay, how about 2 times 255
That's 550.
minus 255?
Minus 2, oh, that's 255.
Yeah, so it increases the amount we're adding, and since we're doing these linear equations, the increase with these bigger numbers is much more, and so it can kind of blow up and things like that. Also, don't you kind of just like numbers 0 to 1, like percentages is 0 to 1,
Oh, yeah.
and stuff like that. And then computers, like I said, they like smaller numbers. So normalizing the data just prevents those like explosions from happening. It just improves performance. You don't have to, but it's very much recommended.
I have a question.
Yeah.
I don't think my code is actually working. Like that PL, that cell.
This one. Also,
You
we
think
don't
you?
need CMap gray. Just move that. Oh, and you can see how the color
Okay.
bar becomes 1 when we
Oh
scale.
yeah, it's giving a name error. Train images is train images is not defined. That's
Yeah, I sent
weird.
them in chat if you need that, but
It says train images is not defined.
is it still defined? Like still not defined?
Let me see.
Like if you copy paste that code in?
Word and to the first cell or which? I mean, in the second cell.
Um, like into the so second cell and the fourth cell.
Yeah, let's see. Oh, that's working. Yeah.
Okay. So now what I'm doing, you guys don't have to type this out, but I'm just kind of showing the first 10 images. That didn't work. Sorry. There we go. So you can see the first 10 images, like just like basic pictures of clothing. Right, and you can see how they're all scaled from 0 to 1. That's just,
Okay, you're using Variant range. I see what you're doing here.
yeah, I'm just iterating 0, 1, 2, 3. It's pretty simple. So we kind of got the data set up. Now let's get the model, right? So the way we're going to do that is using something called sequential. And this is basically going to let us make it almost like building blocks. So you guys must remember that like there's different steps you'd follow. You do the first layer, then the second layer, then let's have an activation function. Say we're using CNNs and maybe you have a CNN, max pooling, then an activation function, then a linear layer, and then output, right? So the way that this lets us do that is it's literally like you stack all of those layers on top of each other in the order you want them to. You can add some specifications and stuff, and then it like couples them together and makes it really easy to use. So you just built a model with super little lines of code. So
Do you
the way we're
need
gonna do
like
that,
layers and like density?
sorry?
Do you need like layers? Like
Yeah, we're gonna
TF
be,
dot keras layers also?
yeah, dot layers,
Okay.
dot flatten is the first one, because
And then it's 28 by 28 if I'm
yeah.
right. Okay.
And the way we see that is we're gonna train images. Let's see the shape of the train images. So 60,000 samples and 28 by 28. We don't like 28 by 28. Let's just have 784. So we flatten it. All right. And then so now we flattened it, and I want to have,
Dense.
did I forget dense? Okay, I did. Let's have the 10 corresponding to the 10 classes, okay? And I'm gonna have, let's have fun with it. Let's have sigmoid activation. If you guys don't know, this is sigmoid activation function.
I use ReLU.
That works too. And then just run that. Oh,
I think try 128 and then activation ReLU and then like do another line 10.
I had an extra parenthesis.
Just copy
I
it.
don't know what that's saying. I think we can ignore that. Okay. Then what we're gonna do is compile the model. So right now we defined how the model should like look like, but we haven't defined what it's gonna use to train. So there's two things we need, or three. We need the optimizer. So what is actually making the weights better? We need the loss. So what is kind of giving the model feedback? What function are we using? And then metrics that we want to show. So in this case, it's going to be accuracy because that's the easiest to work with. So in this case, we're using the Atom optimizer. And basically all the optimizers build off of stochastic gradient descent, which is or gradient descent. And then basically all of them build off of stochastic gradient descent, which is basically a better way of doing it. And Atom builds on top of that and makes it a lot more complex. So the way gradient descent works is it points in the best direction. Stochastic gradient descent wants to add a bit of like randomization into it where it doesn't take insight from all the data. It takes it from a separate chunk each time. So it makes it a little slower, but it lets it avoid like places it might get stuck. And Atom does more stuff I'm not going to get into.
When I tried that model, it's not giving me any output.
What do you mean?
Like if I run it, it just gives me a little check mark, but it doesn't really give like the user the output.
Like this? If
Yeah,
you try to print it?
I'll try. Yeah, okay, now it works, I guess.
Alright. So this is just saying cross entropy is a really common loss function. I'm not going to get too much into it. And from logits is just a parameter we're going to use. And then metrics is just going to be accuracy. Make sure you don't forget the commas. And the reason I'm breaking this up, by the way, is just to make it easier to look at. We don't actually need those breaks. Did I spell this wrong? Sparse.
Wait, what is loss exactly?
It's like the feedback that we're giving. So if you got a test back and you got like a 90%, then your loss would be 10%, right?
Got it.
Loss is like how bad you did, and you want that low number to be as low as possible. There we go. I'll send that code in chat if you guys
Are we expected to like, understand like derive this code now? I mean,
derive this.
or well, of course I don't understand like what it means. I mean, but
What parts do we not understand? Do we understand? We understand imports, right?
yeah.
Mhm.
Do we understand this part?
Uh
I think so.
This
I mean
one's
code like in code syntax, yeah, that makes sense.
you're there's not
where
okay. Oh yeah.
when do we import the like database of like information that we use to train the AI?
We
Oh,
get the
that's what it
data here.
is.
Well, we import the thing that we're getting the data from here, and then we like more better define it here.
All right.
And then that's kind of when we get it, and then we have to load in the data. So I think actually a better answer to your question would be here. This is when we're loading it in, and the output of this function is in this format, and so we just put it in that format.
All right, thank you.
If you guys understand how this works code-wise, that's really good enough because there's nothing like difficult about this. Do we understand this?
Yeah, that makes sense actually.
Do we understand this list?
Mm-hmm.
Mhm.
Do we understand this?
Not completely.
Basically what this is doing is it's going through each and every image and like the first one image, and it's like showing a picture of that image.
Oh, nice. And what does grid equals false mean?
I mean, I can show you. Now there's a grid.
Oh, got it. And what is plt.show? Oh, pl just showing an image. My bad.
Yeah. So if we were to remove that, it might show, it does show, but if I were to do like two images, then it doesn't show the second image. Like it shows on top. And it's just good practice to have plt.show. So now it shows both of them. Okay. Do we understand this?
Sorry, I'm not very good at this stuff. Uh, I don't know. When it says layers, does that mean that like the image is multiple layers and we're all like condensing it into one single layer?
No, it's like a layer of the model. So I think I mentioned in my lectures, like there's the linear layer, which is like the basic neural network layer. Then there's the convolutional layer, and these different types of layers. So in this case, they're the different like parts that the model goes through.
Mm.
It's like you can kind of think of it as like the model's train of thought, and each of these layers is one of those carriages. Does that make sense?
Yeah, that makes sense.
So what
And
we're
what is
doing
dense
here,
for?
yeah.
What is like dense for?
Uh, so dense is there's a lot of ways that people describe or like packages will describe the linear layer, so the fully connected layer, the linear layer, the dense layer, the feed forward layer. Actually, I don't know if they call it feed forward, but it's like a vanilla like basic layer, which is really just like a y equals mx plus b. Uh Actually I'm gonna remove this activation function. So this is just building like what steps the model should follow. So first we're going to flatten the image because we need to flatten the image. And then I'm gonna create a basic neural network layer that's gonna convert all that like 784 information of the data and convert that into 10 values. And this is really where the AI is happening, this one layer. Then we're
What
kind
do you
of
think
putting,
sequential does? I mean, again?
oh, sequential is like, it's like putting the model together. It's like putting
Yeah.
that those layers together in a way that TensorFlow will understand. Otherwise, they're just kind of by themselves and they're not as a model.
Oh, I see.
This is just kind of the building blocks way it uses. Different packages use different ways. They're generally quite similar, but like in
Yeah, that
Python,
makes sense.
you can't just say sequential. You have to say like exactly, you have to use these layers and say like pass the data in through here, then do this to the data, then pass it in here, which gives you more freedom to do things, but it's just much harder and I don't want to deal with that. And I don't think you guys do want to either. Then model.compile. We're basically telling like we're really turning it into a neural network that can learn and giving it some information it needs to learn properly. So you want to be optimizing those weights to give the best output. And so it needs to know what method you want me to optimize them. Let's use Atom. Hey, I need something to give me feedback. Use cross entropy. What should I tell you about how good I'm doing? Use accuracy.
Wait, what's cross entropy again? Like I get it's a
It's
feedback
a
method.
loss function.
Oh, so it just determines how often it's getting stuff right.
Yeah, I'm not gonna. I think like. I'm just not gonna go over how cross entropy works. It's a bit more mathematical and it's really not needed. You don't really need to know how to use it. So we're gonna make sure to compile the model. And then this is just really easy. We're gonna fit the model. So fitting it is basically matching it to the data or making sure it matches. And it's just model.fit. So first it wants to train data. So we'll do train images. Then it wants labels. So what should I be outputting? Just train labels, right? Because we want it to take an image and poop out the label, right?
Yep. And so the labels are the classes?
Yeah, yeah. Classes and labels are basically the same. Classes refers to all the unique labels that are there, and labels refers to like what each image is labeled as. So
Hmm.
what would you label this one as?
Oh, sorry, I'm not. Shoe?
Yeah. So that would be a class. And then the label for this is a shoe.
Are you gonna
Labels,
use epoch?
huh?
Epochs.
Yeah, I'm adding that in. But
Okay.
labels is like for the data, like a specific data value, and classes is for the whole data set. But the values of them are the same. And then we have epochs. Let's do one epoch to keep it simple. Let's do three. So do we know what a epoch is?
No. Sorry.
Okay, so an epoch is the amount of times that the model sees the full data set. So what the model is going to basically be doing right now is it's going to run through all the values in the data set. It's going to say, okay, I'm going to try my best at this problem. Ooh, I got it wrong. I'm going to try the next problem. Ooh, I got it correct. Yay. Getting feedback by the loss function every single time. And it's going to then optimize what it's learned. So it's going to be like, I got this wrong because I forgot to like carry the one. I'll remember to do that next time. And it basically goes through that. And every time it does the same problem set, then it's gonna be like, hey, I'm much smarter now. You know what? I should try again and see if there's anything else I miss. Yay, I got this problem correct. Yeah, I got this problem correct. And it does much better each time and just really makes the model better.
Other than like CPU stress, is there like downside to putting the epochs to like 10,000 or something?
It's slow.
That's
You'll
gonna
see it.
take like a hella long time though.
Yeah, I'll show you afterwards, but so let's try fitting the model for 3 epochs. Let's see how long it takes.
Each takes like a few seconds, or like 3, 4 seconds.
So you can see it started off at 73%, then 84%, then 85%. That's pretty good. And the loss is going down. Exactly what we want to see because the model's optimizing correctly. If you don't
Okay.
see that happening or it's like kind of stopping, if it's stopping, you might be overfitting, or like you're not really doing that well, or maybe the model's like not good enough. That's gonna be a problem. If it's not going down at all and just kind of goes crazy, that's also a problem. That probably means you're underfitting. And then, like say, like going back to your 10,000 question, let's run this again. So let's try and run 10 epochs and see how long it takes. Now, imagine trying to do that for 10,000 times.
It's only taking like 3 seconds. It takes like 5 for me.
Yeah, I think it depends on like the CPU it's running on and stuff like that.
I think I have a Ryzen 7 5800. What do you have?
It's this isn't running on your computer, this is running online. Like this is running on one of Google's servers. So 10,
Oh, I see.
10 of them are done. So think of that 10,000 times. That's going to take quite a while. And you might be wondering, why would I want to do that if it's going to take so long? The accuracy is increasing basically every single time. It's increasing slowly, and so doing tons and tons of epochs will ensure it gets pretty high. And some models really need a lot of epochs before they can get that.
Can you scroll up? I think I missed a couple of lines of code. Oh, like I think I missed them at like the very beginning. My bad. Oh, thank you. Yeah, I missed the dividing function to.
All right. Then what we're going to do is we're going to see the test loss and the test accuracy. And this is through a function called model.evaluate. And this is basically saying like, hey, it's time for the test. You're only going to see this data once and you're going to run through it once. Give me your answers and I'm going to see how good you do. And there's a thing called verbose, which is going to tell us like how much information to poop out. We're just going to set that to 2. But you can see, so 1 is going to be a progress bar, 2 is a single line, and 0 is nothing. So we can show 1 and we can show 2, see what the difference is, and then just print out the test accuracy. And if we want it as a percent, let's multiply by 100. And let's add a percent sign. So we understand the fitting process, right?
Yeah.
Fitting is just like running the data sets, right?
Yeah, running the data sets through the model, letting it understand everything. Do we understand the evaluate? I think it's best if I show you. So you can see there's like a progress bar that runs through. And then finally it prints out that we got 84% accuracy. If I did verbose equals 2, now it's just a single line. It doesn't show that progress bar. That's just personal preference. I prefer verbose 1, so I'm gonna run verbose 1. Does that make sense?
Yeah.
Okay. So now what we're gonna do is create a new model called probability model. So there's a softmax activation function, which basically converts the like output. It's just going to be a bunch of numbers at first to probability to see how sure a model is of a certain class. And we'll see what that looks like. But what we're doing here is currently the model doesn't do that. We're converting it so that it does. It does show that probability output. And again, we're going to be predicting on those test images. We run that. Quickly just runs through, and now we got some predictions. Does this code block make sense?
I thought we
Oh, yeah.
removed the sequential from our like AI.
Sorry?
I thought we removed like sequential from the AI. Did we not do that?
We removed?
Yeah, I thought Yeah, I thought we removed that. Like in that thing where you're putting the density equal to 10, I thought we removed that part.
No, we kept it. This is where we create the original model.
Oh,
Here, what we're doing is we're creating a new model called probability model
oh,
that adds the softmax activation function to the end of model.
and the softmax thing is what gives us the probability?
Yeah, and I'll show you that in a sec. And then probability model.predict just predicts the output. It runs the data through it. So if I were to print out predictions of, let's do 0, you can see it's going to be some very small numbers. And then, see, where's the biggest one here? It's 82%, 88% sure that it's class 9. Right? Again, a bunch of small numbers. And right here, this is like 96.96, right? Just written in scientific notation. So we can see that that's probabilities now. And the way that you're going to find out the one it's predicting is whatever the biggest one is, right? And you want the index of that. So in this case, it's 0, 1, 2. In that last one, it would be 9. And so there's a really nice function for that, and it's just called argmax. So we got 9. Does that match with what the label said? The label also said 9. So in fact, what we can do is we can just go for I in range. Let's do 20. Print np.argmax of predictions. Let's do the ith index and then test labels. Now we can see it's getting it correct for basically everything, but then these two got confused and it got it wrong. Does that make sense?
Yep. Wait, what's argmax?
Argmax, something I mentioned before, but when we have that list of probabilities, we want the biggest probability, right? That's the one it's
Oh,
most sure of. Like if I'm 99% sure of something, then I'm really sure of it. And I think that's what that's what I'm sure of, right? So argmax just figures out which class is the model most sure of for this data. And we can go back and we can use that class names thing. We can use that again. And that lets us say this is the class that it predicted. Put in the argmax. So now it says it predicted ankle boot, it predicted pullover, it predicted trouser. And say we wanted to see what the actual one was. And let's just ignore these numbers, right? Like who likes numbers? So ankle boot, pullover, pullover. Let's see where it gets it wrong. Uh, I can't find it. Oh, sandal and sneaker. So both of them are for feet, so it makes sense that it got it wrong. Do we understand all of this?